union C, because that's what being in this union means. Now this again further can be written like this: x belongs to A or x. Now x belongs to B union C means x belongs to B or x belongs to C. Okay, now what we do? Now just like commutativity, you recall that in mathematical logic we also had associative law or associativity, which says that for three statements P, Q and R, we have something like this. P or Q or R. We will use one half of this, namely this one. Okay, now what is my P, what is my Q and what is my R? This is my P. This is Q and this is R. So you see the pattern, it's similar. You just have to write OR in place of that V. Okay, disjunction symbol. So this implies P or Q or R. So P or Q means x belongs to A or x belongs to B or x belongs to C. This is R. Now this part, what does it tell you? This tells you that x belongs to A union B. With that we have x belongs to C along with OR. Okay. Now from here, I picked up the cap along with this. So from here we then write this implies. Again we have OR, so we can use union. Keep in mind this OR is inclusive OR. Unless otherwise stated in mathematics, OR means inclusive OR. Okay. So this means x belongs to A union B union C. So what have we shown? We have shown that any element x in this set A union B union C is again in A union B union C. That means this set is a subset of this set. In a similar manner, just like what we did in the previous proof, you can prove that this set is a subset of this set by taking any element y in this set and then again doing all the steps in backward fashion. Okay, you have to start from here and then you can come to this, proving that this is also a subset of this. From those two containments, it will follow that these two sets are equal, and that is associativity, associative law. Okay, so that is two properties we have already proved. Now we come to the third one. So what does the third one say? It says actually several statements together. First of all, we have to show that when we take the union of any set with the empty set, we get the set A back. So here, again, you have to show these two statements. I'm not writing proof, okay? So those things can be written down neatly by you once you have understood all the things. I'm just showing you the main ideas. So we have to show this and this. So we start off in the usual way. We take any element in the first set. Since it's an union, this means x belongs to A or x belongs to the empty set. Okay. Now, since the empty set by definition has nothing in it, so this statement is false. Okay, this cannot be true. For no element x is this true. So that means this implies x must belong to A. Because what does disjunction or means? Either this is true or this is true, or both are true. But this is not true. So that means this must be true. Okay. So in this way we have shown that any element in this set is an element in A. So this is a subset of A. Or conversely, if we take an element in A, okay, then this implies, if I write something like this, y belongs to A or y belongs to the empty set. What is the justification for this? How is it that this implies this? If you recall from mathematical logic, there we had something called law of addition, which said that if you take any statement P, that implies P or Q, where Q is any other statement. You can add an extra statement using disjunction. Then the first will imply the second. Since we are adding a new statement, this is law of addition. Similarly, we also have Q implies P or Q. So this is the one we are using here. For us, this is P and this is Q. Okay, so P implies P or Q. And this, of course, again by definition of union, since we have OR, A union empty set. So that's why any element in A is in this set. So this is a subset. So this is also true. So these two containments being true, they give us equality. So in the third property, the first one has been proved. It has been proved. What about the second one? The second one says that A union A is equal to A. So again same, you show this is a subset of this, at the same time this is a subset of this. So you take any element in A union A. This implies x belongs to A or x belongs to A. Now if you remember from mathematical logic, we had something like this. P or P is equivalent to P. This was called idempotence. Idempotence is a situation where you take the same thing twice and do something to them, you get the same thing back. It is somewhat like this. 1 times 1 is equal to 1. 0 plus 0 is equal to 0. Okay. Now 2 times 2 is not equal to 2. So in numbers, these elements are called idempotent elements. Something like that. But in some other situations, like in mathematical logic or set, it is true for all sets. So here what we are, this is our P, this is our again P. Now we are going to use 1/2 of this double implication, that is ordinary implication. So I can just simply write x belongs to A. So I have shown that any element in A union A is in A. So that means A union A is a subset of A. Similarly, if I take, now I have to show the opposite containment. I have to show that any element here is in this set. So y belongs to A implies, by now you already know what I am going to do. So I am going to use this part now. I can write it twice with OR. So this implies A union A. So any element in A is also in A union A. So that means A is also a subset of A union A. Taking into consideration these two containments, we get equality. So the second property in the third property has also been proved. One more is there. So you have seen by now that those properties in mathematical logic, they are being used left and right in proving these properties on sets. In fact, the properties on sets in a sense come from those properties if you think carefully. So the third one is I have to show that A is a subset of A union B. Third one of the third property. At the same time, I have to also show this. Now here I have to just simply show subset, not equality. So it is easier. And I think you can guess what we have to use, which property from mathematical logic. It is the law of addition. This is my P, so P implies P or Q. Q can be any statement. So I conveniently choose Q to be this one. And this implies X belongs to A union B. So this is what proves that A is a subset of A union B. Now I can repeat this with B, but instead I play a trick here. This is important. You see, when you come across something in mathematics, you are being asked to prove something in maths, you don't have to always start from scratch. Sometimes that looks ugly and sometimes that is impossible, practically impossible, because you cannot use something from scratch all the time. It is far better to use what we have already proved in a clever way to prove something else. Okay, much like how you get a corollary as a consequence of a theorem. This situation is like that. Instead of straight away proving this, what I do here, you see, if you how can I explain this? You see the A and B, these names here, they are just names given to sets. Keep in mind that this property is true for all sets. So instead of writing it like this, I could also write the same thing like this, where C and D are sets. As long as the form of the formula is true, what name I am assigning to these sets, that does not matter. Okay, so C is any set, D is any set. Any set is contained in the union of that set with another set. That is the law. These names A, B, they don't matter. Now in place of C, I write B. I can write B because B is also any set, and since this is true for any sets, I can write B here. If I do that, that means what I am doing here is that in place of C I am writing A, and in place of D I am writing B. Okay. In place of C I am writing A. No, I think I have written the wrong thing. I have to write the opposite. In place of C I am writing B, and in place of D I am writing A. Then what does this formula give me? It gives me B is a subset of B union A. Okay, I have not quite got this one, but I have got something similar. But see, I already know that B union A is equal to A union B because union is commutative. So now I have this. So instead of again proving this from starting from scratch, I can use this one itself and derive this one as a consequence. In fact, that is what makes mathematics more powerful and more interesting. You don't have to go from point A to all the points all the time. You can go from point A to some other point, then from there you can go to some other point instead of again coming back to A and making a long journey. That's the point. So this completes the proof of the third property. Now the fourth one is not as direct. It looks somewhat complicated. What it says that A union B is equal to A if and only if A union B is equal to A if and only if B is a subset of A. So if you recall from our previous discussions, I have said that mathematical statements come in two forms. Either they look like this, P implies Q, or P is equivalent to Q. Now this second type of statements are stronger than this one, because here we actually have two implications. This is the same as P implies Q and Q implies P. So we have to prove two things. Okay, so these are stronger statements. They say extra, they say about two implications. This implies this as well as this implies this. So this proof, the proof of this will actually have two parts. In one part, first assume, let us prove the easier one first. In this type of statements, it is most often it is the case that one of these is very easy to prove, but the other is much more difficult, okay, in comparison. So we assume this one. So that means we are first proving this one implies this one. B is a subset of A. Okay. So now I have to prove this. And this again, here what do I mean by proving this? I have to show that this is a subset of this and this is a subset of this. But you already see from the third property, okay, we already know that A is a subset of A union B. Just now we have proved. So I have to show the other containment. A union B is a subset of A. So let X belongs to A union B. So this implies you just apply the definition of union X belongs to A or X belongs to B. Okay, now comes the point where we have to use this one, whatever we have assumed. See, B is a subset of A. That means whenever X belongs to B, X must belong to A. So first X belongs to A stays like that, or in place of X belongs to B, I can write X belongs to A. I won't have place. In such a tight space I cannot write. And this implies what? X belongs to A union A. But we already know, we have proved that A union A is equal to A. So this implies X belongs to A. So see what we have proved here. Any element in A union B is an element in A. That means A union B is a subset of A. You combine these two, A is a subset of A union B and A union B is a subset of A. By the principle of extensionality of sets, you get this. Okay, so having assumed this, we have proved this. And this is the easier part. The more difficult part is to assume this and prove this. So let us do that now. So this is only the first part of the proof. Next, now we have to assume this. A union B is equal to A. We have to prove that B is a subset of A. So let Y belong to B. Okay? Now Y belongs to B. I have to somehow make use of this. So what I do, I apply the law of addition again from mathematical logic. So in place of this, I can write Y belongs to A or Y belongs to B. So here what sort of law of addition I have used? It looks like this. Q implies P or Q. Okay. So that's what I have used here. This again, according to the definition of union of sets, this means Y implies A union B. But according to our assumption, A union B is equal to A. So that means Y belongs to A. So having taken some element in B, I have found that element in A also. So that's why B is a subset of A. So this is the second part. I don't know whether this is more difficult than the previous one or it looks actually easier. Anyway, you get my point. So this concludes the proof. Okay, so the last one naturally will be the toughest one. That's why it's the last one. So this is how all the things have to be proved. The things on sets or the properties of sets. Okay. So that's about union. Now we move on to the next operation. Intersection of sets. For sets A and B, their intersection denoted by like this symbol, upside down U sort of symbol. It is called okay, I'm coming to those things later, what it's called and all those things. So it is denoted like this, is defined as A intersection B. It's called like that, A intersection B. It is the set of those elements X such that X belongs to A and X belongs to B. Or the same thing, you can also write it more simply like this. X belongs to A and X belongs to B. So unlike union, in intersection, we take the common elements and make a set out of them. If there is no common element, then this set remains empty. So this is the empty set. Okay, now we go back to the examples that we considered previously in case of union. For example, if I remember correctly, intersection of these two sets Here you have to take common elements. Okay, x must belong to the first set as well as the second set, and there is only one such element, so 2. What about that one, the second one? The common elements only. So 1 and 2 are common. And what about that complicated one? Here there are two common elements, the singleton set and this two element set. 1 and empty set are not common. So in this case, this is the intersection. When we draw Venn diagram of intersection, it looks like this: A, B. So this much is intersection. You can easily understand why. It's the common area or common region in between these two areas. So this is the intersection of two sets in Venn diagram. Okay, now when we come to intersection, there is a special situation. Unlike union, here there is a special situation. When two sets, when for, okay, not like this. If for two sets A and B, we have A intersection B to be empty, then A and B are said to be disjoint. If two sets have nothing in common, then they are said to be disjoint. For example, these two sets are disjoint. They have nothing in common. But if they have something in common, then also we have a terminology. If A intersection B is not empty, then we say A and B intersect. When you see this phrase, A and B intersect, then you understand that there is at least some common element. Or A intersects B, or B intersects A. They mean the same thing. Okay. So being disjoint means having no common element, and intersecting means having some common element, at least one. So this is just a terminology. It's a term that we frequently use while dealing with sets. Now, just like union, intersections also have some properties. And you can already guess the properties will be similar. For steps A, B, and C, we have number 1, intersection also is commutative. A intersection B equals B intersection A. This is commutative. I'm not writing again, okay? You understand. Intersection also is associative. Right? Third one, if we take the intersection of any element with the empty set, we get the empty set. Take intersection of any element with itself, you get the, any set with itself, you get the set itself. Then intersection of two sets is a subset of both the sets. Finally, A intersection B is equal to A if and only if A is a subset of B. Now, I am not going to prove all of this. In fact, I am going to prove maybe only one, and definitely not the first two, because you can understand. Okay, let me just at least tell you how to prove them. You already know from your experience of proving similar things about union. You can prove these things, but let me at least tell you what the properties of mathematical logic that will be used here in proving these things. When we talk about intersection, what does it give me? X belongs to A intersection B means what? It means X belongs to A and X belongs to B. I am using this symbol for conjunction to remind you of the properties that we had in mathematical logic. There, we had something unlike law of addition that we used conveniently for union. For intersection, we will use law of simplification. If you remember, for two statements P and Q, we had this law. P and P implies Q. Now this law will be used here to prove this one and this one. And of course we have commutative law, Q and P, associative laws for conjunction. Those things will be used here, and this part also will be proved just like the previous one. Okay, so this one I am not doing anything, or should I prove one of them? You get the point. I can try to prove this one, but this will go along the same lines that we had previously. So instead of doing all these things, let us move on to the third operation, intersection of sets. The third operation is difference of two sets. Okay, for sets A and B, their difference A minus B, or it is also written like this, A backslash B. This is called set minus this symbol. But you need not say A set minus B, you just simply say A minus B. Oh, and going back to the symbols, these symbols have some names. This is called cup. The symbol for union is called cup because it looks like cup, and this is called cap. It looks like cap. Okay, but don't go around saying A cup B, A cap B. Although they are not wrong, but they sound strange, weird. You just say A union B, A intersection B, etc. Now, this is the difference. Their difference is defined as A minus B is equal to, it is the set of those elements in A such that they are not in B. Okay. We are subtracting B from A. That means instead of starting now with examples, I show you the Venn diagram and you will immediately understand what this means. A, B. A minus B is the set of those elements in A which are not in B. That means this part. In this part, we have elements in A which are also in B. In this part, we don't have any element of A. So this is A minus B. The elements which are only in A but not in B, they constitute A